This is the most important part. And as you'll see, and to me, any design that you have especially a bone-in growth, it can't break and it can't loosen. Those are the two main things. So during our testing, as I said, we basically validate the fact the base plate met the standards of the ASTM type standards. I will tell you that we had to go back and redesign some things to make it stronger. And we did that, and we were able to do that in record time because the industry or I guess our management realized over the years we've been working with forgings and castings, no longer have to do that. So the speed and the turnaround of the design is really nice from an engineering standpoint. So this is our knee products today. We are looking at different areas for our femoral component. Right now, we still have a beaded femoral component, and our patella is 3D printed, fully 3D printed, as well as that's a hybrid for our base plate. So you see a little bit more of a close-up. It's 1 millimeter thick, a CONCELOC or CONCELOS type structure underneath the surface. And that's printed on the raw material. And here's the porosity that I mentioned earlier. A little bit closer look. As I said earlier, I grew up in the industry where the surgeons just put screws in the base plate. Well, those were no longer going to be something that the surgeons wanted, because that would be what we call osteolysis tracts, and loosening. The base plate would loosen over time as a polyethylene would wear into the base plate. So there was no screws. So at surgery at T=0, that base plate had to be very solid. So we get a press fit. We also get these very sharp corners, which would be impossible to machine, that actually act as anti-rotation devices, if you will, that basically along the keel to help with initial fixation.